This video is designed to help you understand the basic principles of radar, concentrating on two of the most popular units available, the Raycall Decker RD130 and the Vigil Marine Systems RX. The aim is not to replace their manuals, but to enhance the general outline of their operation, detailing how to adjust and interpret the sometimes confusing picture on the screen, and to get the best out of this valuable navigational tool. A modern radar set can be thought of as three distinct parts: a scanner, a control unit, and a display. In practice, though, the control unit may be inside the display or split into several separate sections. The scanner is usually housed in a lightweight plastic casing called the radome to protect it from the weather and physical damage. Inside is the magnetron, transmitting through a revolving aerial which focuses the outgoing microwave pulses into a beam about 4 degrees wide and up to 30 degrees from top to bottom. Returning echoes are picked up either by the same aerial or by a second aerial attached to it. The control unit regulates the transmitter and the outgoing microwave pulses. It also receives the returning echo and ensures that the apparent rotation of the trace on the screen is in step with the physical rotation of the aerial. Daylight viewing or raster scan radars, like the Vigil RX and the RD130, do not have a slowly rotating trace on the display. Instead, the picture appears on a screen like that of a television and is updated about 50 times a second. The control unit has to analyze the range and bearing information it receives and presents it as a suitable electronic signal to the display. All this frantic electronic activity within the set need not normally concern the operator. However, whatever type of radar he has, it will only have 6 main controls: brilliance, range, tuning, gain, sea clutter, and rain clutter. The brilliance control is self-explanatory. It regulates the brightness of the display and should be adjusted so that the picture can be seen clearly without dazzling the operator. On the RD130, this is done by rotating the inner part of the knob just left of center below the screen. The Vigil RX has a push button marked Day-Night, which serves the same function, supplemented by a rocker switch marked Brilliance for fine adjustment. The tuning control can be compared to the tuning knob of a radio. Just as a radio or television has to be tuned to the right station, so the radar's receiver has to be tuned to its transmitter. If it's slightly off-tune, the picture quality will suffer. On the RD130, the tuning is adjusted by turning the outer part of the knob just left of center below the screen, while the Vigil RX has a rocker switch. The range control selects the operating range of the set, which should be chosen to suit the situation. In a narrow river estuary, for example, a long range would cram all the useful detail of nearby objects into a small area at the center of the screen, so a shorter range would be more appropriate. Conversely, when navigating well offshore, a short range would be of little use, but a longer range brings important coastal features into view. The range control on the RD130 is a knob at the bottom right-hand side of the display unit. On the Vigil RX, it's a rocker switch. The gain control is also a rocker switch on the Vigil RX and a knob just right of center on the RD130. It controls the sensitivity of the set. If the gain is turned up too high, the screen will be cluttered by unwanted echoes, such as those from small waves and radio interference. However, if it's too low, weak but genuine echoes will be lost. The C clutter control has a similar effect. So on the RD130 it's a small knob inside the gain control, and on the Vigil RX it's a rocker switch immediately above the gain. In rough conditions, echoes from nearby waves may be so strong that they cannot be eliminated by adjusting the gain without losing more distant, genuine targets. The C clutter control reduces the sensitivity of the receiver to echoes from objects at short range, without affecting the strength of more distant echoes. Although it has a similar name, the rain clutter control operates on a different principle. It should, however, be used with similar care, and in conjunction with adjustments to the gain. Rain, hail, and snow can produce effects on a radar screen not dissimilar to the echoes from land. The rain clutter control reduces the echoes from a rainstorm so that they virtually disappear. On both sets, it's operated by a push button. Before a radar set can be used, it must be warmed up and correctly adjusted. The Vigil RX carries out an automatic starting routine lasting less than 2 minutes as soon as it's turned on. However, just as a human operator would find it difficult to adjust the set with no contacts at all on the screen, or in an exceptionally crowded area, so does the automatic tuning system. Vigil RX operators should be prepared to carry out manual adjustments if necessary. Owners of the RD130, on the other hand, have to carry out the whole switching on procedure for themselves. First, turn the function switch at the bottom left-hand side of the display unit to standby. The aerial will rotate and the magnetron begin to warm up. This takes about a minute, after which the LED next to the function switch will light to show that the radar is ready to transmit. Then, turn the function switch to on. A picture of sorts will appear on the screen. Turn the C clutter control down fully anti-clockwise to prevent it affecting the tuning process, and select a medium range, 8 miles for example. Adjust the brilliance. Adjust the gain so that a background speckle is just visible over the whole picture. Choose a contact near the edge of the screen and adjust the tuning until it appears as firm and as bright as possible. On this boat heading south from Wembury Bay, the radar picture is fairly self-explanatory. The coastline appears on 2 sides of the screen, while the Mewstone Rock shows up as a large echo to the right of centre. The scattered bright spots represent small boats and rocks. Our own boat does not appear on the screen, but is always at its exact centre. The line pointing straight upwards from the centre is called the heading marker and indicates our course. On both the RD130 and the Vigil RX, it can be temporarily removed from the screen by pressing the switch labelled heading marker to reveal any targets that may be hidden by it. The concentric rings provide an indication of range. The distance between the rings depends on the range scale used, and on the RD130 it's indicated by the position of the range knob. Here, with the radar operating on the 2-mile range, the rings are half a mile apart. The Vigil RX displays this information in the top right-hand corner of the screen. The rings can be turned off and on using the switch marked range rings, or simply rings. The picture may be clear, but it's not quite like looking at a chart. Radar waves, like light, travel in straight lines, so parts of the coastline do not appear. They're masked by higher ground. Rivers, for example, like the Yam here, or bays, often appear merely as gaps in the shoreline, details of the mouth being hidden by the headlands on either side. The breakwater appears to have a gap. This is caused by a large ship, S1, obscuring the signal. Land is not the only obstruction which can hide things from radar. Just as ships and land can be lost from view below the visual horizon, the Earth's curvature can conceal them from radar. The radar horizon is slightly further away than the visible horizon, but the effect is the same. Approaching Plymouth, for example, the radar picture does not show breakwater across the harbour entrance. It's below the radar horizon, and the radar is looking over it to pick up higher ground and buildings inside the harbour. There is a simple formula for calculating the distance of the radar horizon. The range in miles equals 1.22 times the square root of the aerial's height above the waterline in feet, or 2.22 times the square root of the height in metres. Parts of the boat itself can also obscure the radar's vision, so it's important to try to mount the aerial above any solid part of the superstructure. A funnel close behind the scanner produces an effect like this, a dark shadow sector at the side of the screen with no echoes, because the radar cannot transmit or receive through the obstruction. Some objects may not appear on the screen because they're invisible to radar. 4 factors influence the strength of the returned signal: the size of the target, its aspect, its texture, and its material. Obviously, a large object will reflect more of the signal than a small one, so you would expect to see a large ship at greater range than a small one. The aspect or angle at which the radar waves strike the target affects the direction in which they bounce. If the target is at right angles to the radar beam, the signal will be reflected straight back. If, on the other hand, it's at an angle, some of the waves will be reflected away from the receiving aerial and be lost. A ship broadside on will appear at a greater range than one heading almost straight towards you. Radar waves striking a rough textured surface, such as a cliff face, will be scattered in various directions. Some will be lost, but at least some will be returned, regardless of the aspect of the cliff. On the other hand, a smooth surface, such as the side of a ship, will act as an almost perfect reflector. So if its aspect is good, it will return a very strong echo. But if its aspect is poor, most of the signal will be lost. Some materials reflect radar waves better than others. Wood and fiberglass, for example, are poor reflectors. Metal is a very good one. For this reason, most small craft nowadays carry radar reflectors designed to improve the chance of their appearing on radar. So far, we've looked at several reasons why objects may not appear on the screen. Sometimes, however, false echoes appear. Fortunately, these only occur at short range and are usually easily recognizable. The glowing arc near the bottom of this screen, for instance, is caused by side lobe reflection. It's virtually impossible to make a perfect aerial, and while most of the radar waves are transmitted in a narrow beam, a few escape at odd angles. These are called side lobes. Though very weak, they can be reflected back to the receiving aerial from a particularly good reflector, and the radar is fooled into believing that the side lobe echoes originate from the main beam. Side lobe echoes can appear on any bearing, but are usually close to the genuine echo and always at the same range. A string of equally spaced echoes on the same bearing like this can be due to multipath reflection. It occurs when the radar wave, already reflected back from the target, bounces off our own boat for a second trip and produces a second echo as a result. 2 ships at close quarters and in line abreast can sometimes see each other as a whole string of echoes, but for small craft, multipath reflection is very rarely a problem. We've dealt with radar's limitations in some length, because it's important that anyone operating a radar knows what to expect from it and how to interpret what they see on the screen. In spite of these limitations, though, it is one of the most versatile of the navigator's tools, with a role to play in both navigation and collision avoidance. Just looking at the radar screen gives some idea of what's going on around us. But for accurate navigation, and to assess the collision risks reliably, we need to be able to measure the range and bearing more accurately. Both sets have the means to do this, though on the RD-130 the function switch must first be turned one step clockwise to the nav position. Range measurements are made using the variable range marker, or VRM. If you have a Vigil RX set, the VRM is brought into operation by switching the range rings off, while on the RD130 there's a knob in the centre of the panel below the screen, which should be turned to the VRM position. On both sets, the VRM appears as a circular trace on the screen, whose radius can be varied by the operator, using the VRM increase and decrease switches on the control panel. The range of a contact is measured by adjusting the VRM until it lies over the innermost edge of the contact. The range is displayed in the top right-hand corner of the Vigil RX screen and on a separate readout in a similar position on the RD130's display unit. Here, for instance, the eastern end of the breakwater is 0.78 nautical miles away. Ideally, range measurements should be taken with the set operating on the shortest possible range. Not only is it easier for the operator to position the VRM accurately on the contact, but the radar itself is inherently more accurate at short operating ranges. On the 2-mile range, for example, the accuracy of VRM measurements is about 40 yards, while at 16 miles it deteriorates to 320 yards. Bearings are taken using the electronic bearing line, the EBL or EBM. This appears on the screen of the RD130 only after the central knob on the control panel has been turned to the position marked EBL. The Vigil RX's EBM is always available. The EBL is a line stretching from the centre of the screen to its edge, which can be moved around the screen by pressing the switches marked EBL increase and decrease. You remember that earlier in this video we mentioned that the horizontal beam width of a typical small craft radar is about 4 degrees. The effect of this is to make small contacts appear bigger to the radar than they really are. This diagram shows a radar signal leaving the rotating scanner towards a small vessel. As soon as the right-hand edge of the radar beam touches the vessel, an echo is reflected back to the receiver. As the aerial rotates, the radar continues to receive an echo until the left-hand edge of the beam clears the vessel, by which time the scanner has turned through 4 degrees. On this screen, the vessel appears to be 4 degrees across. For the same reason, 2 small contacts close together may appear as a large single contact on the screen. When dealing with a small echo, such as a buoy, it's obvious that the EBL should be adjusted so that it cuts through the centre of the contact. The same principle, however, applies to larger contacts, such as land masses, though it's less obvious at first sight. It's tempting to position the EBL so that it touches the edge of the headland. But the radar registers the headland from the first contact of the beam width, not the centre of the beam. Therefore, a more accurate bearing is obtained by moving the EBL inland from the apparent coastline by a distance equivalent to half the beam width. The bearing indicated by the EBL appears in the top right-hand corner of the Vigil screen, or on the digital panel of the RD130. However, unless your boat is fitted with an electronic navigation supervisor to feed information from an electronic compass to the radar, the bearing shown is not a compass bearing. The radar has no means of knowing the boat's course, so the bearing it shows is relative. This contact is at a relative bearing of 108 degrees. To convert that to a compass bearing, we must add the course being steered, 205 degrees. So the compass bearing of this contact is 313 degrees. Still steering 205 degrees, we have a second contact at a relative bearing of 314 degrees. Again, this can be converted to a compass bearing by adding the relative bearing to our course, 519 degrees. As this is more than 360 degrees, 360 has to be subtracted from the result to obtain a useful number. The compass bearing is then 159 degrees. The importance of the course steered gives a clue to the accuracy of radar bearing. The set itself has an inherent accuracy of plus or minus 1 degree. So, if the boat is yawing 5 degrees, the magnetic bearing may therefore be up to 6 degrees out. A radar bearing is better than no bearing at all, but especially in bad weather, it should not be relied on. Perhaps radar's greatest advantage over most other navigation aids is its role in preventing collisions. It's worth reading the international regulations for the prevention of collision at sea to see what special rules govern vessels equipped with radar. Every vessel shall keep a proper lookout by sight and hearing, as well as by all available means appropriate in the prevailing circumstances. So, radar does not excuse you from keeping your eyes and ears open. Every vessel shall use all available means appropriate to the prevailing circumstances to determine if a risk of collision exists. And in case that's not sufficiently obvious, it goes on, proper use shall be made of radar equipment if fitted and operational. But points out that assumptions shall not be made on the basis of scanty information, especially scanty radar information. To save small boat skippers being tempted by poor visibility to break the first of those rules by continually peering at their radar, most modern radar sets, such as the Vigil RX and the RD130, have a guard zone facility, which sounds an audible warning when a contact appears within an area defined on the screen. The process of setting up the guard zone differs between the two sets, so we shall deal with them separately. The RD130's guard zone is a circular band 400 yards wide. It can be set at any range using the VRM. Switch on the VRM using the knob at the center of the panel below the screen. Adjust the VRM to the required range using the increase and decrease switches. Any contact appearing in the 400-yard wide band will trigger an alarm buzzer, and the warning light will glow to show that the guard zone is operating. The Vigil RX's guard zone is more sophisticated and more complicated to set up. In the open sea, it can cover a full circle, like the RD130's. But for use in more confined waters, it can be reduced to cover a specified arc. First, use the VRM to define the inner limit of the guard zone. Assuming a 360-degree guard is required, set the EBM to 0. Press the switch marked Guard Zone. A second VRM and EBM will appear. The VRM will be set to define the required range limit of the guard zone. Finally, press the alarm switch and the chosen guard zone will be operational and shown on the screen. A sector guard zone is set up in the same way, except that instead of setting the EBM to 0 each time, it's used to define the two edges of the zone. Thus, a guard zone can be set up over any specified angle at any position around the boat. The classic indication that there is a risk of collision is when the bearing of an approaching vessel is steady or nearly steady. Most small craft skippers are well used to checking the relative bearing of a vessel by eye-lining it up with a guardrail, window frame, or part of the rigging for a rough check, then confirming its bearing with a hand-bearing compass if it's not obviously changing. Now, the radar equivalent of that first rough check is by means of the EBL, or by using the track facility. Here, a contact has appeared on the screen at 050 degrees. If the EBL is left on that bearing, it will serve as a reminder of the contact's present bearing. Now, a couple of minutes later, the contact is still on the EBL, but its range has reduced. In other words, it appears to be approaching on a steady bearing, so there is a risk of collision. The track facility is obtained on both sets by pressing the switch marked track. Its effect is almost to mimic the appearance of an older style display on which each moving contact left a glowing trail behind it on the screen. Pressing the track switch again removes the track history from the screen. The tracking facility shows at a glance the past relative bearing of every contact, and whether it's getting closer or moving away. On either set, though particularly on the Decker, whose track history is shorter, this is no substitute for proper radar plotting. Radar plotting involves keeping a record of the movement of contacts, either on paper plotting sheets like this one, or with a chinograph pencil on the radar screen itself. Here, Our course is 220 degrees, and we have a contact on a bearing of 050 degrees and at a range of 2 miles. The relative bearing is converted to a compass bearing 270 degrees, and the contact's position marked on the plotting sheets using its compass bearing and its range, and labelled with the time. After a minute or two, the process is repeated. The contact is now 1.5 miles, on a relative bearing of 047 degrees. Our helmsman is yawing slightly, and our course is now 222 degrees, so the compass bearing is 269 degrees. The new position of the contact is marked on the plotting sheet. The bearing has changed only very slightly, so the track of the approaching vessel appears to be heading almost straight towards the centre of the plotting sheet. At a range of 1.5 miles, there is no immediate danger, so there's time to wait a few minutes more and plot a third position. By now, it's obvious that the vessel is not only getting closer, but that its bearing is virtually steady, so there is a risk of collision, and one of us will have to take avoiding action. As we turn, notice that the relative bearing changes quickly. If we continue plotting the contact on the same plotting sheet, the effect of our 30-degree turn to starboard is revealed. Instead of aiming at the centre of the plotting sheet, the contact's track is now heading towards a point somewhere to the south of us. Just how much effect our alteration of course will have on the contact's track depends on the courses and speeds of both vessels, and it's difficult even for an experienced professional radar plotter to predict by eye. It's an easy job to work out our closest point of approach, or CPA. This is the contact's position on the screen at 11:42. 6 minutes later, at 11:48, it had moved to here. Assuming we both maintain our course and speed, its future movement can be projected by extending the line between its past positions. The closest point of approach is here, at a range of 250 yards, at 12:06. So far, we've been concerned only with avoiding collisions, but radar allows us to perform one extra calculation quite impossible to the naked eye. It can be used to find the actual course and speed of another vessel. To start with, let's look at a very simple example. Here we have a contact at 1/4 mile on a bearing of 345 degrees. In fact, it's a buoy, so it's pretty obvious it's stationary. Again, the relative bearing is converted to a compass bearing and the contact's position drawn on the plotting sheet. After 6 minutes, repeating the process shows the contact's relative movement just as before. Its movement down the radar screen corresponds exactly to our own movement through the water, but is in the opposite direction. Now we'll go on to look at a similar situation, but with a moving target. Here it is on the screen at a range of 2 miles and bearing 050. After converting the relative bearing to compass, its position on the plotting sheet is here. After 6 minutes, a second plot again shows its relative movement, just as before. Now, however, we're concerned with its actual movement through the water. We must somehow remove the effect of our own movement from the picture. Imagine that just as we first recorded its position, our contact has dropped a marker buoy. We've just seen that a fixed object appears to move down the screen by a distance equivalent to our own forward movement through the water. So we can work out that the imaginary marker buoy would be here. In other words, its apparent movement would have been in the opposite direction to our own, and it would seem to have covered the same distance. The real movement of the contact through the water over the past 6 minutes is therefore indicated by this line from the imaginary marker to its present position. The traditional method of finding your position when in sight of land involves using a compass to take bearings of 2 or 3 landmarks in turn. Each landmark is identified on the chart and a line drawn from it to represent the bearing of the object. The bearing of Penlee Point is 248 degrees. Our position lies somewhere along the corresponding line drawn on the chart. The bearing of a second object, when plotted on the chart, provides a second position line. There is only one position at which our boat can be on both lines at once, so that point represents our fix. It's normally represented by a circle around the intersection of the position lines. The conventional chart work symbol for a line of bearing is an arrowhead, and of course, every fix should be marked with the time at which it was taken. A third bearing should, in theory, pass through the same point as the other two to confirm the position. In practice, the three lines more often form a small triangle called a cocked hat. The size of the triangle gives some indication of the accuracy of the fix, so a large cocked hat serves as a warning that the fix is unreliable. Using the VRM and the EBL, radar bearings and ranges could be taken and plotted in the same way, although many visible landmarks ashore, such as churches and lighthouses, may not appear on radar. The accuracy of radar bearings is seldom good enough for practical navigation, and it's better to use radar's accurate range measurement instead. Just as in visual fixing, it's important that the 2 or 3 landmarks chosen are clearly visible on the screen and on the chart. It's usually best to choose cliffs or steeply sloping coastlines, or distinct navigation marks, such as lighthouses and lightships. Gently sloping coastlines, such as wide beaches or mudflats, should be avoided, because it's difficult to be certain that the radar echo is really being reflected from the extreme edge of the land. Remember that the edge of a low shoreline may be below the radar's horizon. Here we have Rame Head and Penlee Point. Using the VRM, the range of Rame Head is 0.92 miles, so our position line is a circle whose radius is also 0.92 miles, drawn on the chart using a pair of compasses. Our position is somewhere on the circumference of that circle. The range of Penlee Point is 2.1 miles, and this too can be drawn on the chart. There are 2 points at which the circles intersect, but one of these is obviously wrong and can be ignored. The third position line, or position circle, should pass through the intersection of the other 2 to confirm the position, but it usually forms a cocked hat similar to that obtained from a fix by visual bearings. The symbol for a position line derived from a radar range is an arrowhead on each end of the short arc drawn on the chart. And, of course, the fix is shown by a circle around the position and marked with the time. Ideally, every fix should be plotted using 3 position lines, but there is no need for them all to come from the same source. Visual bearings of 2 landmarks can be checked using a radar range, or 2 radar ranges used in conjunction with a visual bearing. If only one landmark can be seen, a visual bearing can be made in conjunction with a radar range to give a better fix than might otherwise be obtainable. It's sometimes difficult to identify navigation marks such as buoys or lighthouses on the radar screen, particularly if there are a lot of other small contacts in the area. To help overcome this problem, many major navigation marks are now fitted with Raycon transponders. When radar waves strike the transponder, it replies by transmitting a coded signal on the same frequency. Navigation marks equipped with Raycons are indicated on Admiralty charts by a magenta circle and the word Raycon, and details are given in the Admiralty list of radio signals and most nautical almanacs. So, you've now seen how to set up these 2 popular sets and use them. But please don't leave it until you're lost or in fog before using your own set seriously. Practice makes perfect, and familiarity with the operation of your set could prove invaluable when you most need it. So try it out in good visibility. Set it up. See what effect each control has. Use it for navigation and collision avoidance. And then, when you really need it, operating your radar will be second nature.